My name is Brian Putt. I am chair of the energy practice at Probability Management. Today I want to talk to you about converting a crystal ball or an at-risk model to a SIPmath model. While crystal ball and at-risk have many advantages, sometimes it's better to have an interactive model that SIPmath can provide to talk to your decision makers. So let's see how this can be done. In this segment, we're going to talk about converting a crystal ball model to a SIPmath model. Let's assume that we have a crystal ball model that adds up the cost for an IT project. And that cost is broken out into 4 segments: project management, hardware, software, miscellaneous. And each of those has a triangular distribution defined as minimum, with a minimum, most likely, and maximum. Right now, Crystal Ball has set these up as the random variables, and we're going to change that by turning them into a SIPmath random variable. So let's get started. The first thing we need to do is to initialize the SIPmath. We know it needs to be initialized because we don't have any extra worksheets down here. So let's initialize. We'll go to our SIPmath modeler tools. And here's our ribbon with various options, and we're going to initialize. So we initialize. We'll use 1,000 iterations, and we'll say OK. When I do that, it's added 2 other worksheets down here, one PM table and one SIPmath chart data. We are now ready to define our distributions. So we're going to define these distributions right here. So we'll select those cells, and we're going to go to Generate Inputs. And we want a triangular distribution. So here's the triangular distribution. Now we need to define, let's move this over here. Move it over here for now. We need to define the minimum. Well, we're defining 4 things, so we'll need to define 4 minimums. So here are our 4 minimums. And our 4 most likelies. And our 4 maximums. If your data is organized in rows like this, it's very easy to do this. Now for the triangular distribution, it's also asking for a external random cell. So I've set up here a title for the random number because I knew it's a triangular distribution. So I'm going to click in there and highlight these 4 numbers. Now we want to use this Hubbard Decision Research random number algorithm, and it needs a seed. Now we could let SIPmath just assign seeds to it. However, we'd like to do a little bit of control of that. So I'm going to define my own seeds over here. Okay? Enter. So we've defined where the distributions are. We've defined the minimum, most likely, and maximum ranges. We've told it there's a external random cell here and a start variable ID, which is over here. We'll say OK. And we get answers. But you see, all of these are the same. We need to assign different seeds. So what kind of seeds should we put in there? Now, these can be any whole numbers. I think fractions will also work, but I think whole numbers are probably a little bit more straightforward. I'll put in 10, I'll put in 12, I'll put in 18, and I'll put in 30 just for kicks. And now you can see we get different random numbers. These are all independent random variables. If I were to make one of these the same seed, enter, you can see I get the same random number. Then they'd be correlated. So we'll undo that. We'll put our 12 back in. Okay, so now here is our sum. So we'll put a sum right here. We'll say equals the sum of these 4 things, right? Now, we are interested in this distribution. So we're going to define outputs. And we have to give it a name. Let's call it D underscore total. And the reason I put D in front of it is for distribution, and it says total. Now you can call this anything you want, but if I use a D in front of all of my outputs, then I know that they are distributions and they're vectors. The define outputs has defined the distribution of total over here on our PM table. We now have 1,000 outcomes of total. I'll hit Shift and down, and we can see that that's called D total for a distribution. All right. Now what we'd like to know is, what does that distribution look like? So we'll come up here and we'll do a graphs. And let's define this for 21 bins. Gives a little bit more definition. And we'll put a histogram right over here. And we'll put a cumulative distribution function over here. And we'll say OK. And there are the distributions for total. We have the histogram and the cumulative distribution function. Let's do one more thing here, and that is we want to get some statistics on this total. So over here we're going to say equals average of total. Oops, we want D total. I can just click on that and it gets D total. And over here I want the percentiles for total, P10, P50, and P90. So I'm going to say equals percentile. I'm going to use the EXE. If you have an older version of Excel, you may not have the EXE option, and you just need to convert back to percentile. But because we're using from a sample, the .exe is the right statistic to use. We'll put in total here, D total, comma, and we'll just highlight this percentile here. And then I can pull that over. And there are the P10, 50, 90 for total. I'll put the title over here. Total. So this looks pretty good. Now let's just check something here. It says the P10 is 62.32. And if I look over here, the P10 is something less than 61. So this cumulative distribution graph can be somewhat misleading. So in the next segment, we'll talk about how to build a better cumulative distribution function.